Bismillahirrahmanirrahim. Assalamualaikum and very good day. We'll continue with the next subtopic, integral method. So this is the second method, how to determine the rate of reaction. So let's look at the description or explanation related to this method. The integral method of analysis always put a particular rate equation to the task by integrating and comparing the predicted C versus T, concentration versus time curve, with the experimental concentration versus T data. So if you look at the figure on the right hand side, so this is an equation in terms of concentration as the y-axis and time as the x-axis. So if you look at the circle point here, so that is the experimental data. Okay, while the solid line, that is the model or the linear regression equation that we get it from the equation by integrating the relationship between concentration and time. All right. Look at the second point. If the order assume an appropriate plot, the concentration time data will be linear. So we are talking here we are referring to a linear model, right? If it is happen to be not linear, so meaning that either the data cannot be fit to the models, so you cannot use this method, or something wrong with your experimental data for which you need to repeat it again. The third point, if the fit is unsatisfactory, another rate equation is guessed and tested. This procedure is shown and used in the cases next treated, meaning that we are going to assume an order first. Okay, let's assume it is zeros order. Okay, you do the integration of zeros order equation, you get an equation, then you feed the data to this model. So let's look at the R square, the linear regression coefficient. Is it fits? Fits here means it'll give you satisfactory values of R square, more than 0.95, I suppose. Or else, if you are comparing four order, zeros, first order, second order, and third order, for example, choose the highest linear regression coefficients among these four. So meaning that your experimental data can be fitted to that order. All right. Meaning that you need to do try and error. Start with zeros. If it is not satisfactory, then proceed with the first order. If not satisfactory, let's say you get 0.4 R squared, then move on to the next order. Last point, it should be noted that the integral method is especially useful for fitting simple reactions types corresponding to elementary reactions. Okay, so it's very useful for elementary, meaning that when it is elementary, automatically you may know what is the order. Okay, you are given, okay, A plus B, you get product C and D. Then it's mentioned the reaction is elementary. Okay, it's elementary reactions, meaning automatically you should know that negative RE, BK, CA, CB. So it is second order reaction. So second order meaning that you will straight away integrate the equation according to second order assumption. That's it. Okay, by having that, basically for the order is already solved. the unsolved parameter will be value of K. All right. So this is basically the algorithm. Okay, we'll start first with gas direction order. Once you guess whether it's zeros, first, second, or third, then you proceed with integrate the differential equation. Okay, the word integrate, that's why the method is called integral method. Next is plot concentration versus time. Example in the previous slide. If not linear, try guess other reaction order. If not linear, or you have very low or low R square, linear regression coefficient, R square very low, example 0.3, 0.7 is still considered low. Okay, the best is to have 0.95 and above. Alright, if it is not satisfactory, and repeat it again. Guess another reaction order. It's quite straightforward. But as mentioned in the previous slide, if the problems already mentioned that the order of reaction is an elementary, meaning you already come with the solutions. You already have solutions. What's order of the reactions? You are going to only try to find what is the value of chemical reaction equation, chemical reactions constant. So this is the equation. Okay, if we guess is zero order, okay, meaning that this is most of the time we put negative RA equal to K CA power of 0. Okay, but in this slide they move negative sign to the right hand side. It doesn't matter. It's just mathematics. Okay. So since Ca, the concentration of the species A, that is the key reactant, power to 0, it become 1. Alright. So combine rate law and material balance. Okay, this is your rate law. Material balance, that is your dCA over dt equal to Ra, or you may have the negative sign. Alright. Or you may drop it. So in this case, they do drop it. Okay. Okay. For the first reaction, Ra is equal to negative K, and then Ra is also equal to dCA over dt. Then you'll combine. Okay. Combine, what you have is dCA over dt is equivalent to negative K. This equation. Okay, moving further, the next step is to integrate this equation. So by now, you should practice yourself to do the integrations. If the problems involve integral method, then you need to show how you carried out the integration steps. Alright, for this case, it's quite straightforward. You are going to integrate both sides. Okay, from where to where? We write it somewhere here. So let's put it dCA equal to negative K. K is a constant, you may put it outside. So this is dt. So integrate both sides. From where to where? It's supposed to be from CA0 to CA. Initial to the final. Initial concentration of species A to the final concentration of species A. From T0 to time to T. Remember, this is batch system, right? You need to have certain duration of time. that is your reaction time from 0 to t. So integrate, you should have CA. The limit will be CA naught, go to negative K, and then your T will be from 0 to T. So you are going to CA, upper limit minus lower limit. So it will be CA minus CA naught equivalent to negative K T minus 0. Okay, simplify, it will be CA minus CA naught go to negative KT. Right, so this is the equation. What you need to do next is to plot a graph. Remember, to plot the graph, and it should be a linear relationship. Linear relationship meaning this is your y, okay, and which one is your x? You need to have a slope, right? So the available data for batch system, obviously the concentration and the time. So T will be your x. K will be your slope. CA naught will be your intercept. The same concept you are going to apply for the rest of assumed order. Okay, so basically the graph will be, this is your CA, this is your T. Then it should have an intercept. Your intercept should be CA naught. And then the slope should be your K. Then solve. You know what is a K. Then if you get a very good R square, meaning that is your K from the slope, and then it's correct to assign the order of the reaction as 0. Okay, move on to the first order. If you assume it is first order, so this is power of 1. Alright, combine rate law and material balance. We combine as what we did for zeros order, and then do the integration. Okay, the step for integration, it is in the next slide. As for this one, what you are going to do is to plot ln CA naught over CA versus T. Is there any intercept? No. There is no intercept, meaning the intercept is at 0, 0. Okay. This equation also can be represented as, if you write ln CA over CA naught, then you'll have the negative sign. It doesn't matter. This is just mathematics. Whatever you get, whatever plot that you are going to prepare later, obviously the slope is negative sign, but at the end, the value of K should be a positive value. Alright. Okay, this is the plot as I mentioned earlier. Right. Yeah, this is a correct representation because negative slope, you should get this kind of trend. Okay, it is decreasing trend because it's negative sign of slope. And for first order, I already discussed this earlier in the previous slide. In this slide, the order gas is second order. So this is the equation, second order. The next step is to combine rate law and material balance. Okay, from the material balance, we know that RA equal to dCA over dt. Okay, now dCA over dt is equal to negative CA squared. Next is to integrate the equation. So I need you to spend time to do the integration by yourself. Remember, not only for this chapter, later there are a lot of integration. If you cannot familiar with these steps, it's gonna be very difficult for the next chapter. Okay, integration for this one, we may rearrange this so that there'll be 1 over CA squared dCA equivalent to negative K T K dt. Alright, next is to integrate both sides. Negative K is a constant. You may put it outside of the integration. Okay, this equation also can be written as CA negative 2. Integration again from CA naught to CE, as this is a batch system. Alright, so what is the integration of CA minus 2? CA power of negative 2. So it will be plus, right? For integration, you need to plus power plus 1. So negative 2 plus 1 will be negative 1. Then you need to multiply by the negative. So what you have is negative CA negative 1. Alright, then you may put it this way. It will be 1 over negative 1 over CA. I just do it step by step. It's up to you. It's better to show it step by step. If not, someone will say that you are copying from somewhere else. Okay, then substitute the limit. It will be negative 1 over CA minus negative 1 over CE naught negative K T. Okay, and then this will be equivalent to, because let's take this positive value at the front. So what you have is 1 over CA naught minus 1 over CA equal to negative K T. Okay, upon rearrange this equation, it's up to you. If you want to leave it like this also, you may plot the graph, or you may rearrange it as a given in the slide also. In the slide, they remove the negative sign at negative K, meaning that everything here you need to multiply by negative. This one also multiply by negative. So it become 1 over CA, because it becomes positive, minus 1 over CA naught equivalent to KT. So this is the plot. Okay, the dotted line, the dotted point here, that is the experimental data. So the solid line, that is the theoretical relationship according to this equation. Okay, so having that, the slope will be equivalent to K, and the intercept will be 1 over CE naught. Alright, so this is the integration method for first order. We already discussed this one. If you want to have a look again, then you may spend sometimes nothing, not so much different compared to what we already discussed in the previous slide. Okay, you look at this box in red color outline. Okay, this is in terms of X. Okay, what we did just now is all in terms of concentration. you may have it also in terms of conversion. Okay, how? We already know what is the relationship between X and C. Okay, this is upon rearrange. It's actually come from, for batch system, it's come actually from X is equal to NA naught minus NA divided by NA naught. Alright, then you may divide by volume since you have a constant volume. Then you'll get CA naught minus CA divided by CA naught. Okay, so this is equivalent to this equation, whereby CA naught divided by CA naught is equal to 1. Okay, then rearrange the formula. Then you may have this equation. CA is equal to CA naught 1 minus X. Alright, so if you can imagine a batch reactor, let's say you have concentration of 10 molar. Okay, initial. A final for species A is 1 molar, meaning mole per liter. So you should be agree if I said that CA is equal to CA naught 1 minus X. So in this case, X is equal to, conversion will be 0.9. We already discussed this one earlier. If 10 to 1, the conversion will be 0.1 according to this equation. It's 10 minus 1 divided by 10, 0.9 or 90%. So CA is equivalent to CA naught. So CA naught here is 10, 1 minus 0.9. So 1 minus 0.9 is 0.1 multiplied by 10 is 1. So by knowing what is the conversion, you may also calculate the final concentration. Done. Okay, the next box. Okay, this is actually in terms of differential form. Okay, it's very useful. It's very useful, this equation. I did show how you differentiate this equation. Quite straightforward. You have X 1 minus CA over CA naught. Again, it's come from the base equation. And then differentiate. So dxa over dCA is equivalent to 1 over CA naught. Okay, upon rearrange, it's not really clear here because they have letters here. It will be negative dCA is equal to CA naught dXA. So this is the relationship whereby if you have this kind of equation and then you want to have it in terms of X, what you are going to do is to substitute negative dCA with CA naught dXA and then do the integration. Okay, spend some time how to do the integration for the equation in terms of X. Okay, so if you look at the integration here, integration of 1 divided by 1 minus XA is ln, negative ln, in bracket 1 minus XA. Alright, by now I want you to use your calculator, utilize your calculator, because having this kind of integration, sometimes it's not necessary to know what is the equation. You may use your calculator to punch all the equation and the calculator will provide you the answer. Alright? Okay. If we have a face-to-face lecture, I always suggest you to have the latest model of calculator. Can't remember what is the model, CHE502 something 960. Okay, they have the integration feature. The earlier version or earlier model also they have the integration, but it's not as user friendly as the latest model. Okay, because latest model you can see the integration symbol. In the earlier model you cannot see, and then it's very useful also for ChemThermo. ChemThermo, you are going to integrate a lot of numbers, values. From my experience, the previous model they have limited number of character, for which the latest model you can have more. I don't know what is the limit, but we never encountered the limit. As for the previous model, yes, up to certain character cannot go anymore. All right. So in this slide is relating X and C, conversion and concentration. So you are going to apply the same principle once you integrate it. So this is the equation. What you are going to do next is plot a linear relationship. So your Y will be this one, X will be your T. So this is K will be your slope. Okay, you may read this description. A plot of ln 1 minus xe or ln CA over CE naught versus T as shown in the figure give a straight line through the origin for this form of trade-off equation. So this is for first order. If the experimental data seems to be better fitted by a curve than a straight line, try another rate form because the first order reaction does not satisfactorily fit the data. Alright. Not only in this course or chapter, even in research also we employ the same principle. Okay. Especially when we are dealing with a new substance, new products, or we develop a process with new reactants. Okay, you need to know what is the rate constants and what is the order. So this is example in Fogler, page 269. Integral methods of CRE, chemical reaction engineering data analysis. Use the integral method to confirm that the reaction is second order with respect to triphenyl methichloride as described in example 5-1, and to calculate the specific reaction rate K prime. Okay, basically this is similar example. You are working on the similar data. Okay, example 5-1, but using different method, that is integral method. And here you already mentioned it is second order, so your assumption will be the second order. All right. Then you integrate, you'll get the linear relationship after the integration. But remember, in this example, it's supposed to be negative RE K CA CB. Remember, when CB is almost equivalent to CB naught, for which the methanol is 10 times higher in concentration compared to the key reactant A. Okay, for which you are going to simplify the equation to have K prime is equal to K CB naught. Okay, that's why you have a K prime here. If you can recall this one, then you may go back to the differential method explained for this example. Alright, if we see the reaction indeed a second order, then plot 1 over CA versus T should be a linear. So this is the data, process data. It's already calculated with for you. In the graphical solution, the data in the table can be used to construct a plot of 1 over CA as a function of T, which will yield the specific reaction rate K prime. This plot is shown in figure CHE502.1. Again, one could use Excel or Polymath to find K prime from the data table. The slope of the line is the specific reaction rate K prime. So since we are having our lecture, our teaching and learning activities by open and distance learning. So I suggest instead of you use a graph paper, use Excel. Okay. This is the third method, how to determine rate law and the rate constant by initial rates methods. Okay, for this subtopic, I will provide you another video. As for now, I want you to try, not only try, to do the integral methods. Use example 5-1. Okay, even though in the previous slide already it's already give you the process data. I want you to redo it, not only for second order, but for zeros, first, and zero and first, and also for the second order, meaning that you need to derive the equation by integration, and then I want you to plot it using Excel. For this task, I want you to do it in pairs, similar pair for which you did the previous exercise for the differential method. Okay, that's all for now. Assalamualaikum.